Hello, all. Welcome to another episode of AWS Show and Tell. Thank you for joining us on a Tuesday evening. I'm Anil Nadiminti, your host, joining today from New Jersey. Joining along with me is Lana and Brandon. I am a senior solutions architect here at AWS, and I support enterprise customers. I'm also in the agentic, technical field community within AWS, agentic AI technical field community, and we'll go through quick introductions here. Lana.
Oh, hi. Hi, everyone. My name is Lana Zhang. I'm a senior solutions architect from AWS Bedrock specialist team focused on Nova. Nice to meet you today.
Thanks, Lana. Brandon.
Hey folks, nice to meet you. My name is Brandon Naya. I am a senior product manager on the artificial general intelligence group, primarily focused on our Nova multimodal embeddings model. Some exciting updates we have for you that we're looking forward to sharing today.
Great. Thanks. Thanks for the intro, folks. And for anyone who's connecting, let us know where you're joining us from. We have folks connecting from across the globe who listen to the live stream to catch up with some of those demos, the cool demos that they're waiting to see. Today's topic is about Nova multimodal embeddings. And if you have done semantic searches or retrieval augmented systems, this is the topic that you'll be most interested in. And Brandon and Lana are here to talk about the state of the art embedding model, right? So state of the art. So Brandon, you want to tell us what this is all about?
I will happily do so. Let me first maybe set some context in terms of the genesis of how we actually went about prioritizing such a model. So I think we all know this, but we live in a world that's very unstructured in terms of the data that we have all around us. We've recently seen from an IDC report that approximately 90% of the data of enterprise data is unstructured, and that unstructured data is growing more and more and more. And it makes it really challenging for customers and for companies to really tap into that value that's hidden within unstructured data. There isn't really a really easy way to extract those kind of insights. And what we wanted to do was to really try to get closer to customers to allow them to tap into that value and unlock just new different types of use cases that they can use to generate, just better insights for their customers. And so, there's three kind of challenges we were trying to unlock with, looking into a truly native multimodal offering. The first was really, we have all this unstructured data. It lives through all of these different types of content types. So finding a single way that allows us to extract those insights across the different content types and brings them together. The second one here is we really wanted to have a way to allow you to search and reason across unstructured data. And lastly, we wanted to make sure that we can do this in a scalable way, a way that's price performance, a way that allows you to access the ability and really unlock those use cases for your customers.
So on the first case, right, where you mentioned the unstructured data, Brandon, or there, maybe if you want to give some examples of that data, right? So we have different kinds of unstructured data, but if you want to break it down for our viewers there.
Yeah, absolutely. I think as you typically, you can think of, being in an enterprise and you may have, PDF documents that contain text and charts, and those range, from 5 years ago that's sitting in a vector store somewhere. You may also have a training video that have, visual components. It may have audio components as well. You may have images in a different location. You may have speech data in a different location. You may have just text files, text-heavy documents sitting in a particular data repository. And again, because of the nature of all these different types of data, firstly, it's not easy to actually extract those insights, even if you're just looking at one content type. But it really starts to compound when you're looking at it across the board, across the different kind of content types. And so when we talk about unstructured data, that's really the challenge that we're looking at trying to address.
And also, I mean, when we're looking at these documents, some of these documents have PDF, but in between the text, we have images, right? So I was even working on these demos, working with other customers, and we're like, hey, all these, it's good to be able to understand all these PDFs and text within it, but being able to search, within documents that have a combination of these modalities, right? So there's a lot to unpack there, I guess.
Yeah. Yeah, it's actually both. It's the challenge between having, a mixed modality repository where you have maybe, images or videos and audio, but also you have very complex objects too, right? Like you gave a really great example of a PDF document that has, images, which may have, text. You may have a chart. That chart may also have text in it, right? You can think about like the chart title or even just anecdotes that are placed on the chart. That's an example of a really complex multimodal document or object that we are trying to maybe like search or reason over. So that's kind of the nature of the challenge that we are trying to address.
Yeah, thanks for that overview here.
Yeah. And so the reason we started looking into vectors is really as a way to try to use vectors as a way to address that kind of unstructured nature. A lot of questions might be asked in terms of, what is a vector embedding? And, really simply put, a vector embedding is just a way to take an input, such as an image, and to represent it in a machine readable language. It's what we called an embedding or a vector embedding. Take, for example, this lovely Labrador that we have on screen. It's a dog sitting on a beach, and it has a blue bandana around its neck, and it has, very happy or smiley face. As we as humans try to perceive this image, all of those different insights are something that we use to really understand the context of the image. You may look at this image and think fun day at the beach, or happy dog, or a memory of your own dog maybe. A vector embedding is generated by taking this particular image, passing it through an embedding model like the Nova multimodal embedding model, and the output is represented as a vector, as, in another word, a bunch of numbers that actually capture all of those intricate details that we just went through. And because it is a machine readable language, computers can use this language, use these vectors, relate them to one another, and try to find semantic similarities, or compare different vectors to try to find if there's any kind of common threads or information that can be seen between them. As we move on to like the Nova multimodal embeddings model, this is a brand new model that we came out with just 2 weeks ago. We launched the model as GA on 10/28, and it is the industry's first unified embedding model. By that, I mean it takes in images, text, documents, audio, and video, and it's able to process it all through a single model. So you don't have this kind of data silo or fragmented approach where you have your images sitting in one location, your text sitting in another location, and your video sitting in another location. It's a single model that allows you to extract insights and reason across these different types of complex inputs. And the benefit of having a single model is that it really is able to keep the same translation or the same meaning across the different types of entities. So we can go back to the example of the dog sitting on a beach. You may have that particular image of a dog sitting on a beach. You may have the literal text, dog sitting on a beach, or you may have background audio of a dog barking. These all have very similar types of semantic meaning. When we think about it, we have a relationship that we associate them very closely together. And in that same way, when you pass those three different types of inputs, the image, the text, and the video with the dog barking, they are represented in a very similar format within after passing through the Nova multimodal embedding model. And this makes it very easy now to actually compare and contrast them, because you can cluster them together, or you can search for something like saying, find me a picture of a dog or find me a video of a dog. and it extends across the different modalities. So you don't have to have that kind of siloed approach.
So you don't need to have like separate vector stores or separate embedding models for each modality type, right? And you can use one embedding model and just calling it as a unified embedding model.
Exactly. I think, like, as we are looking through these customer use cases, what we typically found is that most of the embedding models on the market were very much specialized to just one or two modalities. So they might have solved for text and images, or maybe text and video, but Nova multimodal embedding solves for all of those through the same model. The challenge is, if you have separate models, you have to try to find a way to create some kind of relationship between the meaning between the different models, which is not very easy from a technical standpoint. And we typically find customers would either try to make that investment or just settle on a particular use case. But Nova allows you to expand your use cases or expand your horizon so that you can still maintain the same kind of experience irrespective of the modality that you were trying to look through. The second key benefit that we think through as we're looking at Nova multimodal embeddings is that even though we have such a comprehensive offering, a model that's truly multimodal in nature or natively multimodal, we still maintain leading accuracy. And so we compared Nova multimodal embeddings against all of these different specialized models, and we still are able to obtain really great performance from a retrieval perspective. And later on, I'll show you a bit of the model card, and we can go through what those figures might look like. And the last component to this is, as we think of powering semantic search or RAG workflows, it's really important to make sure that you're able to do this at scale and at very low costs. And so with Nova multimodal embeddings, we're pretty proud to say that we have pretty leading costs when you're trying to generate these kind of embeddings. And so you can actually invest that money in other aspects of your application to make sure you have a good use case for your users. I'll take you through some of the key features of the model, and then we'll go a bit into like some of the performance characteristics. So as I've mentioned, we have extremely comprehensive coverage across all of these different common enterprise content types. We also provide 4 different embedding dimensions or embedding lengths. The embedding dimension is just a way to get a sense of how densely you want that information represented. So we use something called Matryoshka representation learning, which is really just a way to try to maximize the amount of context that we place into the earlier dimensions. And so if you wanted to truncate from a 3,000 length vector down to a 256 length vector, you minimize that accuracy drop. So you don't really see much of a difference from an accuracy perspective if you wanted to go for a small dimension. Like I mentioned, we also wanted to make sure that we really cater for scale when we built out this model, as well as the API systems supporting it. And so Nova multimodal embeddings comes with both a synchronous API as well as an asynchronous API. You can think about your asynchronous API as something that really handles your large files or your batch workloads. This is really when you're trying to create an index. Maybe you have, images in the order of millions. You want to create an index. It's really a latency insensitive process, so it doesn't really impact your end user's experience. You pass that through to an asynchronous API and generate those embeddings. We also have a synchronous API, which allows for much quicker retrieval times. And so here you can think about a typical search use case where your end user might be typing in, find me the image of my dog, and you want that result to be returned very quickly so that it doesn't interrupt their experience.
So one thing when we create these embeddings, Brandon, is we need to store those embeddings, those vectors, in a vector store, and we have vector store support in AWS, right? So can you speak about where we could store these embeddings within AWS?
Yeah, exactly. So a key component to the success of your embeddings is definitely the vector store. AWS has a host of different kind of services that allow for great vector stores. Some examples could be Amazon OpenSearch. They provide very performant embedding both storage as well as retrieval. Amazon S3 Vector Store is currently in private beta, and they are also a great option where you can, at a very low cost, you're able to still maintain really great performance from a vector store perspective.
Yeah, S3 Vectors is one of my favorites to utilize the vector stores because it's number one, cost effective, performant. So you can have like millions of documents in S3 and then generate the embeddings and store them right there, be able to scale that.
Yeah, definitely. The last component that we offer also with the API is, as you think about trying to create an embedding from very large files, it's not always suitable to take a long video, for example, and try to generate a single vector. There's just too much context that you're trying to bake into the vector, and you may miss some of those key characteristics like chunking support. And this allows you basically to take in, for example, you can bring in an hour-long video and you can segment that or chunk that into smaller partitions, and then generate an embedding for each of those partitions, still allowing you to retain some of that semantic context in a very rich way.
Amazing. So which means that we can break up, the model will take care of splitting that into smaller chunks and allow the storage into the vector store.
Exactly. We also provide a pretty comprehensive, range of capabilities that we handle via the API as well as the model. First, I'll just detail the context window. So Nova multimodal embeddings comes with a pretty high context length. It's about 8,200 tokens. So if you're thinking about it from a document perspective, you can take a pretty a large number of document pages, extract that text, and create a single embedding from it, and you can still get pretty high accurate representations. If you try to translate that into video or audio, it's approximately 30 seconds for each of those. And for an image or a document image, it will be about 1 page or 1 image each. I also show on screen just the range of formats we support. Again, we want to make sure that it's very easy for you to extract the insights from all the different types of enterprise content you have. And so we provide a pretty wide range of support across the board. The model is also multilingual. And so if you're thinking about trying to do different types of use cases across different types of documents in a different language, with Nova multimodal embeddings, you're able to do so. We support up to 200 languages. And like I mentioned, we have both a synchronous and an asynchronous API, as well as batch inference support that allows you to generate your embeddings at scale. So just going back to the problems that we tried to highlight at the beginning, we have a world with unstructured data that we're trying to tap into across all of these different types, be it text, images, documents, video, or audio. Nova multimodal embeddings helps you to solve that because it is a single embedding model, the first embedding model to do so, that's able to generate embeddings across all these different types of content types and still represent them within the same semantic space, within the same meaning. We allow you to provide, pretty accurate search and retrieval results to power those semantic search applications or RAG applications. And lastly, we go through, some of the key benefits of having those different types of APIs, as well as the price to match it to allow you to not only scale up your applications, but also to do it in a very cost-efficient way. This is the last slide I'll present, and it's a little bit about talking through how does the model actually perform. And so when I started this conversation, we went through that a lot of the existing models tend to cater to one or few modalities specifically. And so when we tried to compare the performance of Nova multimodal embeddings, we wanted to pick the best of the best to really look against how does it actually perform. And we have a range of benchmarks here across video retrieval, audio retrieval, visual document retrieval. And so, as we were speaking about earlier, a document that has both text and images, as well as just plain images like the image of a dog, and lastly, text retrieval. And across all of the benchmarks, we do see leading accuracy, especially compared to what alternative offerings might be offering. If you look at video retrieval and audio retrieval, as well as visual documents, Nova Nova Multimodal Embeddings really stands out as an accurate offering that can still deliver the cross-modal functionality, but still provide really great accuracy. For images and text as well, we pitted the model against some of the best models out there, and comparable, you can see that the model is still delivering really great results at that point. I think it might make sense to also go through some demos to really showcase what the model might do when you actually put it out in the wild. And so, Anil, maybe it might be good to pass it on to Lana, and we can take it there.
Yeah, I mean, folks are here to watch those cool demos, right? So, and make sense of what we are chatting here. So, Lana, now it's time to present all the demos that we have. So, take it away.
Yeah, my pleasure to present the Nova multimodal embedding demo. So let's start it from a simple search use case, right? So if you go to a website, you want to search, the classic way is usually keyword-based search. You pre-label your content, right? So for example, on the screen, I have a collection of shoes, boots, sneakers, right? And then they already attached with labels, so you can search efficiently. So for example, if I'm typing sneaker, it brings up sneakers. If I'm typing boots, it brings up boots. I can do like a little bit more. It works pretty well. In the use case, you can predict what you want to search, and the benefit of that is usually it's fast, right? So keyword is basically key value pair. From the database level, it serves a good performance. But sometimes users have more contextual search. So for example, I'm just typing in like, let me zoom in a little bit. The Cairo boots, let's go with everything, right? So in this case, it doesn't really match any keywords. Therefore, I couldn't find anything. So this is a time semantic search, like embedding powered semantic search start to shine, right? So in a similar data set, so you also can search sneaker.
So while we are searching, Lana, so what is semantic search, right? For the viewers, if you want to break that down.
Yeah, semantic search is like powered by the embedding, right? So let's circle back with a little architecture here. So like Brandon earlier elaborated on how the embedding works, right? So we have this ingestion process. So basically, it could be image, video, document, text files, right? So we are using the model to generate vectors and then store those vectors into the vector store. So for this demo, I'm using vector S3 vectors. It could be the other vector store, such as OpenSearch, Aurora, and Redis, and also on AWS, there's a collection of third-party vector store available as well. So that's a process you bulk inject all your data into the database, right? So in my demo, I already have those data injected. And then the search process, which is similar, but it happened in real time, right? So for example, I'm typing a keyword sneaker, it's generating embedding using the same model, and then it search against the database, right? So it's pretty much a similarity search. So this is my input vector. In the database, you have a collection of vectors, which ones are most similar, right? And then from here, you can include more semantic meaning, right? So rather, instead of being super precise, like the key value search, you can describe context. And then because the mechanism under the hood is bring up the most relevant, most similar result, so you can get a relevant result. Switching back to the demo, right? So let's try the previous search phrase. Doesn't work for key value pair search, right? So just paste in casual boots that go with everything, right? It lists me a collection of boots, which I may like, All right, so that's multimodal search, right? So we just demoed a simple one, which is using text and search, in this case, image, right? So let's see another one. You can input the other modalities to search against your inventory, right? So I'm showcasing a simple one, which is searching using an input image, right? So let's say this is an image I have in mind. It's my dream boots. I want to buy something like that. I can upload it to my website and then to search. And then under the hood is similar mechanism, right? So the process takes this image using the same model to generate embedding and search against the database. And you can see the one bring up on the top, it does look very similar as the image I provided, right? So similarly, the process also works for video clip input and audio input, right? So you have a sample clip of video, you want to find out from your inventory which videos are the closest, then that's the way to go. All right, so that's search, right? So which is one step away from RAG, if you're familiar with the terminology, retrieval augmented generation, right? So basically, I provided the input, I generated embedding, I retrieved the result. On top of that, if you apply generation, then it's RAG, right? So the model will take this response and then it generated some human understandable result to me, right? So let's see some simple sample.
Mhm.
So for example, it's still here. So this is more a semantic video search. So my question was, if you don't see it, an animal-shaped robot climbing on the roof, right? So, and then in my inventory, I already have some videos indexed. Under the hood, NOAA multimodal embedding segments the video, breaking down the video into smaller clips and store the index. So when I search, it brings up the clips, which is closest to my input, right? So you can see this clips returned from certain video, which is started after the video started 15 seconds to 20 seconds. And then this is the one have a robot climbing on the roof.
So if you want to pause there for a second, right, and then maybe let's zoom out for a second. So what you did there is you entered the text. So behind the scenes, the embeddings got generated, and then a comparison search was done, a similarity search was done to an embedding store, which already converted the all these uh, documents, or in this case, the videos, into embeddings.
Yeah,
So
yeah,
we were able to find the exact clip of where the robot was climbing on the roof.
yeah, absolutely. This is more like a slightly different application design, right? So you can use it to search. You can use it in a chatbot scenario, so it's more interactive with human. Um, So another example, this is more the classic RAG situation, right? So I'm asking question, what is Amazon Nova? So it's similarly, take this text, generate embedding, search against the database, and then it retrieved a few segments. Those are the citations, right? So it retrieved from the vector database. And then Nova using, this is chatbot, using this citation to generate a response. So it tells me it tried to answer my question based on the citation it retrieved from the vector store, and also it showed me the raw citation, right? So if you're familiar with RAG-based chatbot, this is exactly how it works. Yeah, another example is document search. So this is a question I'm asking is, can I use a voucher to take an AWS certification exam? Right, you can see it bring up some document screenshots. So for example, this one is ranked on the top, right? You can see one of the section it mentioned is free practice. If you can see the text, right? So you prepare for your next AWS certification using a practice exam voucher, right? So this is exactly the page I'm looking for. So this is how NOVA multimodal embedding work with document. Last but not least, it's a image search example, right? So my question is a volleyball game in which the red team is attacking while the blue team is defending, right? And then you can see it bring up some relevant images about the basketball, about the volleyball. And then this one ranked on top of that because the thing is closer to my search phrase.
I see that you've highlighted the distance, which shows which one is more closer, and so that one gets more preference.
Yeah, yeah.
Sorry, the ranking of that is higher.
Right. So distance is more this one because in the database we use a cosine distance search. So the smaller, the closer, right? So for if you're using other algorithm in some database, it could be the larger, the closer.
So which means, Lana, so all your videos, documents, they can be in different data stores, but the embeddings can be in one data store where you're going to hit the embeddings model, get the response back to figure out where it is, and then show the images here, right? Is that what's happening in your sample architectures?
Right. So it's basically it's a little architecture discussion, right? So
Right.
basically, you have a vector store to store your vectors and serve the efficient search. Along with that, most of the database allow you to store additional metadata, right? So it depends on the database, the type of metadata is differ. In my case, I'm just
Using S3 vector.
yeah, and then metadata. I have the file. For example, my file is stored on S3, so it has S3 bucket, S3 key. Additionally, the file name and some other metadata, right? So that's the flexibility offered by S3 store. But if you use some more advanced, like more powerful database, for example, OpenSearch designed for extremely low latency type of search, it offers more flexibility. Along with your vector, you can having more rich schema um, like metadata, right? So it can be a trade-off. So we run into this type of debating a lot internally. One of the best practice we could try to share is you should separate your vector store and your metadata database, right? So a lot of case when you build, it's easy just to manage them in one place, but they actually have different nature for search and also have different requirement for scale, right? So a best practice is to separate your database so you can in production you can scale them accordingly.
That's great. And all the samples that the Lana is showing, I've linked them in the chat, so you can go to GitHub repo and then pull the samples and get started.
Awesome.
Excellent. So is this the demos that we have today, Lana?
Yeah, we can show a few more if there's interest.
Yeah,
Uh,
I mean, cool, excellent. So I mean, we could do that, or we could say that we've presented on the multimodal use cases. Let me see if we have any questions. Here we have one, right? So Andres is asking a question. I wonder how much resource it takes to index all videos to be able to provide clips for separated topics like robots on example roof.
the question about the resource, I'm thinking is more like computer resource, like memory, CPUs,
Storage, maybe in this case.
storage. So yeah. So it's the benefit of utilizing. I will let Brandon to elaborate. Is managed by the API, right? So because the asynchronous API is designed for batch process, the application usually like the demo is you have your video available on S3, and then you just invoke the API through Bedrock to the multimodal embedding model from Noah, and then Noah will do the heavy lifting. It will take this video, do the segmentation, generate vectors, and then there's an asynchronous task. When it's completed, it will return a vector to a S3, like which you specified when you make the request. And then your applications just take these vectors, which is a JSON file, and then index them into your vector store. So it's a very light on the application. It doesn't require very high like CPU memory footage. Brandon, you want to add to it?
Yeah, I guess we might have some internet issues there,
Mhm,
but
mhm.
yeah, with that said, any takeaways for our viewers, Lana? This is the state-of-the-art model uh, that has the capabilities to create embeddings for all different kinds of modalities, documents, images, video, audio, right? So, any takeaways for our viewers as they explore agentic AI RAG use cases?
Yeah, absolutely. As always, my recommendation is give it a try. The best way to learn is by building, right? So multimodal embedding is a powerful tool, can benefit a lot of different use cases. Like video embedding is one of the I've been focusing on. So it can help you with really rich like DAM, like digital asset management, media asset management type of requirement for the media industry, right? Also for advertising industry, for example, they have large inventory of ad creatives, so they need to label this. The traditional way is to label all this content, so to serve search. But the challenge will be from time to time the trend change, right? So in whatever you labeled 2 years ago, down the road, no longer valid, or there's new trend, you don't want to reprocess all your video to just generate a few labels. So in this type of case, embedding is very practical, right? So because you store the embedding into the database, which is suitable for more ad hoc query down the road. Yeah.
Thanks, Lana. So, Brandon, we were just discussing about the key takeaways, like for our viewers, as they start exploring those, use cases for embeddings.
Yeah,
So, yeah, any closing comments there?
I think a couple things I wanted to call out, especially from Lana's demos, is you would have seen a pretty big difference between your standard keyword matching or keyword search, which is typically when we think about searching, we inherently go for that. We inherently go for blue shoes, and we expect to be able to find just a blue shoe. But really, what we want to do with vector-based search or embedding-based search is twofold. One is we want to get more semantic. So you get to, you don't always want to find an exact copy, but you want to start to find content that's more based on its meaning. So more on the nuance side of things, right? You can think of, how would we define a gloomy day? That's a great
Right.
example of like, unless someone has tagged something as a gloomy day, there's no real way to know it's a gloomy day. But we as humans intrinsically know that. And so the model also provides that capability. And the second aspect that I think that Lana's videos also highlighted is, we can also get a lot more complex in terms of the types of queries that we're looking for, right? So it's no longer just doing, find me blue shoes, but it's, find me the team that's playing volleyball where the red team is doing X and the blue team is doing Y. That's a really complex search. And to be able to find all of those nuances, all of those characteristics, and to retrieve that one is just a sense of how truly multimodal we can get, how truly we can understand what the content actually represents. And I think that's cool. I think it can unlock, a bunch of use cases for us to really get much more in tune for how we want to search versus how we're kind of just know how to search based off our own history.
And the fact that it supports 200 plus languages, right? So is a game changer. Being able to search across different languages, modalities. So, folks, if you want to go ahead, give a try. The links are in the chat for you to explore, and the sample Git are in GitHub. They're also available for you to play around. Definitely explore more of the Nova multimodals. So that's it from us this week, and we'll see you next time on the same AWS Show and Tell channel with another topic. Thanks a lot for tuning in. That's it from our side.
Thanks so much.